Alright, Math 3. I'm going to fill out some notes on tangent lines. Tangent lines. So we remember from our vocabulary the other day that tangent lines touch a circle, or intersect is a better word, touch the circle in exactly one place. Okay, so here we have a picture of a tangent line. Here we have a picture of a tangent line, and that point that it touches is called the point of tangency. Alright, so just to highlight that, point of tangency is right there. Okay, we're going to find out just by looking at this picture. You can probably see what's going on, but tangent lines are perpendicular to the radius or the diameter at that point of tangency. Okay, so a couple things to remind you of. Of course, perpendicular means they'll meet at 90 degrees. The symbol for perpendicular looks like this. And of course, sometimes we use the word right angle. It meets at a right angle. So you can see I have the right angle right here. Now, what we do is we use this line of tangency, and we go ahead and add an extra line in right there. And what happens? What did we just create? Well, this creates a right triangle, doesn't it? And we like that it has a right triangle because we know lots of things about right triangles, including the Pythagorean Theorem. So the Pythagorean Theorem is very commonly used with circles and tangents. So just anticipate that in the future. A couple examples to look at below. All right, here, I know these circles don't look like circles. They're a little bit out of scale. My drawing's got a little stretched. I'm sorry about that. So anyways, let's check this out. I'm asking you if these lines are tangent. So what I'm asking is this line right here tangent? Okay, this one is the one that appears to be tangent. So the tangent line has to be perpendicular to the radius. So that puts my right angle right here. So I try to use the Pythagorean Theorem. And my question is, does the Pythagorean Theorem work? So I'll go ahead and try it. And you can see that, yes, the Pythagorean Theorem did work. 169 equals 169. Therefore, that line is tangent. So basically, if you want to know if something's tangent or not, then you want to know, does the Pythagorean Theorem work? Another example, same idea. So over on this side, which line is tangent? Okay, it's this line. So the radius would be right here. And notice the radius is actually only a 6. I gave you a 12, but the radius itself is only a 6. But that also tells us where the right angle is. So these are the two legs, and 10 is the hypotenuse. So try the Pythagorean Theorem. And you can see that once again, the Pythagorean Theorem worked. And if the Pythagorean Theorem works, then in fact it is a tangent line. Okay. We'll go on to the next ones and check that out. You guys should stop as often as you need and go back and review. Alright, so this time I'm going to find missing segments. Okay, so we're going to look at this picture to start with. First thing I need to do, it does say assume that lines that are tangent are tangent. So what I want to do is I want to assume this is the line that I believe is tangent. So I'm going to assume it is tangent and say that it's perpendicular. Well, because it's perpendicular, that gives me a right triangle. And on that right triangle, I'm going to use the Pythagorean Theorem. To find out that AC has to be about 9.4. Just follow through my Pythagorean Theorem. AC is 9.4. Now, my second question is to find DC. Now notice, DC is this little piece right here. Alright? So I just found that to be, but DC is this little piece. Well, if the whole piece, AC, is 9.4, how am I supposed to find DC? Well, what I have to notice is AD is a radius, just like AB is a radius. So if AB is 5 and the radius is 5, that means this also has to be 5. And because now I know that's a 5, I can subtract to find out that DC has to be 4.4. Alright, chew on that for a while and take a look. We're going to check out these. Remember, lines that appear to be tangent are tangent. So I believe that this line is tangent, which means that's the right angle. So I'm going to use the Pythagorean Theorem. And that should give me the length of A. All right. Over on this example, once again, anything that appears to be tangent is tangent. So I believe that the 16 is tangent, so my right angle is right here, which gives me the Pythagorean Theorem. Okay. And notice that I could not say it was x squared. X is only this tiny little piece on the outside. C is actually the whole hypotenuse of this triangle, so I had to create a new variable here. We're going to solve that for C first. When I do that, I find out that C has to be 20, but that's not what they asked me for. They asked me for x. So, up on my picture, I know that C is 20. Once again, this little piece is a radius, just like that is a radius. So that little piece is 12, so I can take my 20, subtract the 12, and get 8. Take your time to look at that. There's one more rule we need to look at with tangent lines. Now I told you during class we did not have a chance to go through this. I will go through it now. And I told you if you watch this at home, then you get all these answers to fill it in. I've given you a picture of two tangent lines to the same circle. They both come from the same point C. Now what we're going to do is I want you to draw in AD and AB. So I'm going to go ahead and do that. Now AD and AB are both radius, right? So it's actually radii. That's just plural for radius. Therefore, AD is congruent to AB. They're the same. Aren't all radii the same? CD and CB are both tangent to circle A. Therefore, angle CDA and angle CBA are both, how many degrees? 90 degrees, because it's perpendicular. Now, I asked you to draw in AC. There was AB from earlier. So I draw in AC. Right here is AC. And I hope you recognize I have triangles now. Now, I did recognize that those two are perpendicular. I have triangles now. So since AC is congruent to itself, we can say that AC is congruent to AC, right? And now we go into some Math 2 proofs. By the what property we can say that those two triangles are equal? Do you recognize we have two triangles that are equal to each other? Okay. You've told me that they're both 90 degrees. You've told me that the two radiuses are equal. And you've told me that AC is equal to itself. So I hope you recognize that this triangle here and this triangle here are congruent to each other, and that is by what we call the Hypotenuse Leg Theorem. So we can say that triangle ADC is congruent to triangle ABC. And because I have two triangles that are congruent, I now recognize that DC and BC must also be congruent. And we call that CPCTC, or in other words, corresponding parts of congruent triangles. congruent. All right. And again, the abbreviation for that is CPCTC. All right. Now that leads us into what we've already done here. We know that two tangent lines from the same point are, here was what we filled in class, congruent to each other. All right, take a moment to pause here. We're going to do an example. Oops, there's congruent. Congruent to each other. All right, 3 examples to look at here. This one's pretty straightforward. If these two appear to be tangent, and they are, then they're congruent to each other. Therefore, x is 12. Very straightforward. Now, you'll never, ever, ever get a problem that easy, but that is what we just learned. Now, what we're going to do is we're going to take this situation, and we're going to see that situation in this picture. So, do you see right here the triangle where we have tangent lines? Every side of this triangle is tangent to the circle. Okay? Now specifically, AR and AQ. Doesn't that look like this? So if AR is 4, what does that tell us about AQ? That it is also 4. Looking at the entire length, I can find QC by subtracting. So since the whole thing is 11, I could subtract this 4 and get that that's 7. And now, in green, do I recognize that this situation here is the same? Two tangent lines, and they both come from the same point, so those two must both be 7. And then over here, I recognize that these two must be the same, so they're both 3. Of course, the answer was find the perimeter, so I can just add all that up now and find out that the perimeter is 28. One more to look at, and that's over here. Again, assume lines that are tangent appear to be tangent are tangent, so these appear to be tangent. So because these appear to be tangent, we know they are equal to each other. So I simply write down the 2 equations. And I solve. And I find out x is 9. Now, that's really all I'm asking you for is x here. I could go further and ask you some more questions, but really that's the end of that situation. Now, some people in class did ask for a little bit further, so we could, substitute in and find those out. You can actually find the radius of this now if you want to, but you don't have to. So, since we found out this is 9 and this is 15, and I know this is tangent, that makes a right triangle. Now, the radius is unknown. I don't know the radius, so I'm going to call it r, but notice I have a radius here and a radius here. So I'm going to use the Pythagorean Theorem. And so far, you get that r squared and 15 squared has to equal, my question is, how long is this? And that is r plus 9 squared. Now, this is a good Math 3 problem because now I have to square this binomial. So if I FOIL out the binomial, I get this. I subtract the r squared, and something lovely happens. What I thought was going to be a quadratic problem, what I thought was quadratic isn't, and it ends up being pretty quick. I can solve for r now and find out that the radius has to be 8. Once you know the radius is 8, I could ask you all sorts of questions. I could ask you about area, I could ask you about circumference, anything. I know this was a little bit longer. Take your time, run through it as many times as you need to, and we'll see you in class.